but it's going to save you a whole lot of time in the long run if you just memorize that k times p, or k times the variable acting as y, is going to be an exponential function. So where this is going to kind of lead us and what we're going to kind of compare this to is what we call the logistics growth equation. So I'm going to kind of compare the two because I think it's best to introduce them by comparing the two. So the one that we already know is for exponential growth, and it comes from the differential equation that is worded dy dx is directly proportional to y. Whenever you see that statement, you know then that it is going to be an exponential equation. The dy dx, again, directly proportional to y. And then you've memorized that that's just going to become dE to the k times x. Again, one way to do it, separate the variables, integrate both sides, and kind of go from there. But it is going to be a lot easier if you just have memorized that kind of shortcut. That differential equation is going to describe exponential growth, and it would look something like that. Logistic growth is going to be related. It's honestly the more realistic one for a lot of different situations. Because when we talk about exponential growth, we're saying like, hey, this thing is like growing exponentially forever. Like it's just always growing. And in real life, yes, things might have exponential growth, but they usually slow down as it reaches a certain number. Like you can think about populations and like, I don't know, this comes up a lot in like biology, where like, say you have some population of, I don't know, bacteria in a petri dish. Well, those bacteria cannot just keep increasing exponentially forever. There's going to be like some cap of like, this is the maximum number of bacteria that can live in this environment. Or if you do something just more generic, like, I don't know, like rabbits in a field, like there's only a certain amount of population that that field can handle. So the logistic growth equation starts off as an exponential, but then kind of bends and reaches like this maximum value. To introduce some like vocabulary words, you might recognize this from science. That maximum value is called the carrying capacity. And it's basically like the maximum value allowed. We're typically going to be talking about like a population when this occurs. The setup for this problem is still going to be a dy dx problem, but instead of being directly proportional to y, it's going to be directly proportional in the way that it is worded. And again, I'm looking at my notes just to make sure I word it correctly. Yeah, the product of y and I'm using this expression L minus y. It typically won't be given to you in that format. What L is representing, that L is going to be the carrying capacity. And for whatever reason, we're going to use a capital L to kind of represent that carrying capacity. So what that equation gives us is going to be the differential equation for logistics growth. And that differential equation is basically going to be directly proportional. So it's going to be K, and it's directly proportional to the product of Y and L minus Y. I do want to say something about that equation. So the definition of logistic growth is directly proportional to the product of Y and L minus Y, which does give us this differential equation, but it's often not the differential equation that is as useful or kind of often see on the AP exam. So I'm going to call this like K sub 1 just for a second. We're actually going to kind of manipulate it and rewrite it. And the way that this will often show up in the one that I actually want you to memorize is when that L is actually factored on the outside. So if I factor out this L, I'm pulling the L on the outside. So that's going to be L times K sub 1y. And since I factor out that L, that's going to become 1 minus y over L. Again, I factor that L out from the parentheses. K sub 1 is the constant of proportionality. L is the carrying capacity, also a constant. Well, what is a constant times a constant? Just another constant. So I'm going to call that one just the K, y, and then 1 minus y over L. That's the version I want you to memorize because that's how the AP exam is going to write it. So like, yes, mathematically, this one is correct. That is from the definition of logistic growth. The best one you want to memorize is going to be that version where there's like a clear K in front of the Y, and L is going to end up being in the denominator under the Y. And then we are just going to memorize what that Y is equal to, and I'm going to put that on the next slide because this one's getting a little bit messy. So again, first thing we're going to memorize, yes, we have the exponential growth. For the exponential growth, dy dx is ky, which is going to give us y is equal to de to the kx. Memorize that, use that shortcut. For the logistic growth, dy dx is equal to this ky times 1 minus y over L. And what that is equal to is this equation. And it's going to be y is equal to L over 1 plus b e to the negative kx. Memorize that and it will save you a whole lot of time. So basically what we're going to be looking at today is kind of two things. How we interpret both this equation and this logistic equation, and then also how we move from this differential equation to that logistics equation. And again, we're going to memorize and jump straight to that y. If you want to see where it comes from, like be my guest is kind of complicated, and you're more than welcome to try it, but where that y actually comes from is if you separate the variables and then integrate it, you actually have to do like partial fraction decomposition, which we don't have time to do. Like on the AP exam, you're not going to have time to do, / no one wants to do. So again, it's just going to be easier for you just to memorize when you see that dy dx, this is what that y is going to become. And then you just have to basically fill in the coefficients. And you will notice that some of the coefficients are the same. So like this k right here is the same as that k. This L is the same as that L. And then B ends up being the only constant you have to solve for. So again, memorizing those two forms, it's just going to be like plug things in and then go from there. So again, what do each of those variables represent? That K is called the constant of proportionality. Unlike the exponential one, where we had to often solve for it, for the logistic one, you're often given the equation, so you can kind of figure out what it is just from the equation directly. The L is the carrying capacity, which you kind of already mentioned. And then B just doesn't have a name, it's just another constant. So the first thing I want to look at before we start solving questions, just from looking at some of the old exams and some of even like the multiple choice and the free responses, instead of often like solving these problems, they just want you to be able to match them up. So they might give you a graph and say, hey, which one of these equations could possibly be this graph? Or they'll give you a slope field and they'll say which one of these slope fields would match to this differential equation. So the first thing we want to be able to do is kind of talk about, like, as K changes, how does that affect the graph? As L changes, how does that affect the graph? And then as B changes, how does that affect the graph? So I will just tell you it because I'm just like memorizing stuff, but I am going to switch to Desmos right now. There we go. And so I have graphed a logistic growth equation. So I type that into Desmos, and then I put sliders on for L, B, and K. In general, you want to understand what the graph looks like. Like you'll never have to graph it by hand, but you do want to be able to kind of like be able to match up an equation to a graph. The general equation, it has a horizontal asymptote at 0, and then a horizontal asymptote at the carrying capacity. So you can kind of imagine L is the easiest one to do. As L increases, that upper asymptote is going to increase. As L decreases, that asymptote is going to decrease. What's also important about L, and I'll see if you can kind of see it. So I'm going to leave B is at 1 right now. So this point here on the y-axis What point on the graph would we call that using some first semester terms?
Why?
It is a y-intercept. Let me ask a better question.
I'm just like, I don't think it's supposed to be.
Yeah, let me ask a better question. What's the concavity to the left of that point? Concave up, and then to the right of that point,
What was the point of inflection?
concave down. That's the point of the inflections. Let me find a better way to ask that question. Is a y-intercept. That is the point of inflection, and this graph will always be like, as long as it's an increasing one, starts off being concave up, and then changes to being concave down. So sometimes they might ask the question like, hey, when is this logistics equation concave up? And you just know it's going to be concave up on like the first half of the graph. When is it concave down? Those know that it's concave down on the second half of the graph. I do want you to look at that point of inflection. That point of inflection will always be halfway between the two asymptotes. So basically that lower asymptote is 0, that top asymptote is L. You can kind of see like as L changes, that point of inflection is always at the halfway point between the two of them. K, let's talk about that one next. For most of our problems, K is going to be positive because we are typically talking about logistic growth. As K increases, kind of like an exponential, it just becomes a steeper and steeper logistics equation that still has those asymptotes. As K switches to be negative, then it just turns into a logistic kind of decay function. So positive K increasing, negative K, it would be a decreasing one. Again, typically we're going to see a positive one for these problems. And then your B value, I think this one is like the least intuitive. So B is a constant, like we usually solve for it with an initial condition. If you look at the equation, it's like the coefficient in front of that exponential term in the denominator. How that translates on the graph, so B equals 1 is kind of like no transformations, and that point of inflection is on the y-axis. As B gets bigger than 1, you can see that point of inflection is basically shifting to the right, still halfway between the two asymptotes. As B becomes less than 1, then it's moving it to the left. B will not be negative ever, so if you do get a negative B, you did something wrong, because I can kind of show you. When B is negative, then it's no longer a logistic growth equation. So B will always be positive, basically between 0 and 1, shifting it to the left, and then bigger than 1, shifting it to the right. So to summarize all this, to go kind of back to the notes, let's review what each of these does. So K is the constant of proportionality. Biggest thing you want to know about K, when it is greater than 0, then that is going to be a logistics growth equation. When K is less than 0, then that's going to be a logistics decay equation. Again, growth would be like concave up, then switches to concave down. Decay would be concave down, then switches to concave up. So that's going to be an easy way to kind of match up those equations. We know that L is going to be directly the carrying capacity, which shows up as a horizontal asymptote on the graph. For us, we're not going to have like any vertical transformations. So like one of our asymptotes will always be the x-axis. Again, that's not true for all logistics equations, but for us, it will always be 0. And then the carrying capacity will always be the second one. So like if L is 10, it could look something like that. If L is 5, then it's going to be shrunk down and look something like that. Other key things we'll notice, that point of inflection, depending on how it's been shifted, is always going to be at L divided by 2. So like I know for this first graph, the point of inflection will be when y is 5. You might have to solve to figure out where the x is. For the second one, I know the point of inflection would be at 2.5. And then we have this value of b. The value of b does affect the horizontal kind of transformations of it. When b is equal to 1, that is when the point of inflection will be on the y-axis. And then as B changes, that will be basically where we see our horizontal shifts. If B is 10, then we're basically have shifted over that point of inflection by some amount in that positive direction. If B became something like 0.5, we would be shifting it the other way. Why we want to talk about the graphs is a lot of times in these problems, it will ask you to interpret the graph, and you will be expected to know what the graph looks like. For example, if y is a logistics of growth equation, so if y is a logistics growth, things the AP exam might expect you to be able to find, it might ask you to find some limits of your logistics growth equation. So like maybe the limit as x goes to infinity or negative infinity. And this is where you have to kind of know what the graph looks like. Again, it wouldn't be provided probably on like the no calculator section. But it's pretty easy. Like if you're going towards infinity, what's going to be the limit of that function? L is going to be approaching the carrying capacity. If you're going back towards negative infinity, what's going to be the limit? 0. If it's a growth one, because it's going to be approaching 0. So again, knowing what the graph looks like is important. Another question I see a lot of, I'm trying to think of some of the old questions. Sometimes it asks you like, where or when is the fastest growth? Or it might ask you like, when is the function the steepest? Visually looking at the graph, at what point does the graph look to be the steepest? At the point of inflection. So you just have to know that that's going to occur at the point of inflection, which is of course when the y coordinate is half that carrying capacity. It's always going to be between 0 and the carrying capacity. So a lot of this topic, we're not going to worry about like there's not going to be like doing sign charts or like actually find the second derivative. You just have to know what the graph looks like to save you time, which is why you want to kind of know what those variables do. And the first problems on the homework will have you kind of practice all those as well. So let's go ahead and look at an example. And this is actually the last time I'm going to do today. I'm going to have you do most of your problems kind of just practicing in the homework. For a lot of these questions, when it is a logistics growth equation, it will not look automatically like a logistics growth equation. So like I know we're doing it on the logistics growth day, so like clearly this one is a logistics growth, but it currently does not look like a logistics growth equation. If it was in a logistics growth equation, and I should be clear, if it's a differential equation, you do want to make sure you have that form memorized. And again, the memorized form is dy dx is equal to ky times 1 minus y over L. This does not look like that format, but you do want to be able to recognize when you can get it easily into that format. Some clues that you can get it into that format easily is you will typically have a y and a y squared term, and you will often have two terms being subtracted. So if I'm looking at this differential equation, to me, and I know I've been doing this a lot longer, that looks like a logistics equation because we have a y and a y squared term, and they're both being subtracted. We also know that once it is a logistics growth equation, then we don't need to do any work. We can jump straight to what the y is equal to. And again, you would have this memorized. And y would be L over that 1 plus b e to the negative kx. Which is why it's important to get it in that form, because once you get it in that form, you clearly see what k is, and you clearly see what L is, and then your initial condition will help you solve for e. So if we're looking at this differential equation, what algebra would you need to do to basically manipulate it to turn it into that desired format? Factor. And again, the big clue is we often want this to be a 1. So you basically just want to factor out whatever you need to turn that number into a 1. So for this one, what are we technically going to be factoring out of it? 2/3 of y. So we're going to factor out 2/3 of y. And on the inside, that first term is a 1. We do have a y left over. And then just make sure you do your numbers correctly. So it was like a 1/18. If I factor out 2/3, that's the same as multiplying by 3/2. 3/18 is 1/6. And then times 2 in the denominator will give you 1/12. Now we've clearly put it into the logistics growth equation. How is that useful? We now know for certain 2 of our values. What do we know k has to be? 2/3. K is 2/3. What do we also know L has to be? 12. And again, that's useful. Say maybe this was a question that said, hey, match this to the graph. We already know this graph will be increasing. We know it's an exponential, a logistic growth. And we also know that that upper horizontal asymptote is a 12. So again, knowing how the graph and those pieces play a role is definitely useful. So I'm going to go ahead and plug into that equation. So I have y is equal to L over 1 plus b, which we'll need to find, e to the negative kx. And now we just want to find b. Go ahead and use our initial condition. Y is 4 when x is 0. So I have 4 is equal to 12 over 1 plus b e. Well, negative 2/3 times 0 is 0. What's e to the 0th power? 1. So don't make this math harder than it needs to be. 4 is equal to 12 divided by what? Well, let's solve all the way. So I know you can see that's going to be 2. But 12 divided by 3 is 4, because sometimes it's not always going to be that easy. 12 divided by 3 is 4. So I know that denominator has to be equal to 3. Well, e to the 0th is 1. So what does b have to be equal to? And then 2. So typically, they're not going to be hard equations to solve. So what will be your final answer? Y is equal to 12 over 1 plus b, e to the negative 2/3, which is your k, negative k, and then x. And so that would be the equation. Again, I don't have any follow-up questions to this. That's where I kind of want to make sure you do the homework and the practice, but things I could ask you, like, what is the limit of that graph? Like, as x goes to infinity or negative infinity, I could ask you for the location of the point of inflection, or I could have you, like, create an equation to solve, like, what is x when y is 10, or what is y when x is a certain value? Yes, sir.
Won't the limit to negative infinity always be 0 if we're not dealing with any horizontal asymptotes by the x-axis?
Say it again.
Wouldn't the limit of y as x approaches negative infinity always be 0?
It will always be 0, yeah.
Okay.
So like the only time it wouldn't be 0 is if you had something added on the outside, which for us is not going to be a thing for our logistics. Yeah. But for us, it's always going to be basically, I know horizontal asymptote is at 0, and then the upper one is at 12. And then a point of inflection would be at 6.
Okay.
So that's basically what we have for the logistics equations. Again, you have to have those formed memorized to make this easy for you. But that's basically all there is to the logistics equations. Before I take any other questions, I was going to show you, I do have one word problem. It's a moose problem that you can kind of see in OneNote. It's optional, but I might strongly encourage you to at least look at it before your test on Friday. It's a good question to look at because it covers everything from like tangent lines to Euler's method to logistic growth. Like if you can do that problem, like you're going to be pretty much set for your test on Friday. And the key for it is shared with you in OneNote. I don't have it here, but it should be shared at the bottom of your notes page. So what I want you working on is basically your homework. So at this point, you should be done or almost done with homework 4. And then now you can go ahead and start that homework number 5. Homework number 6 is optional. I do have that marked in OneNote in case you just want some extra practice. But basically tomorrow and Thursday, we're just reviewing and getting ready for our test on Friday. And then next week we get to start convergent and divergent series. So y'all can go ahead and get started on the homework. Definitely if you have questions, let me know. And I'll go ahead and start with people at home. So like you're good to go.